Hello everyone, and welcome back to our channel. Today, we're diving into a groundbreaking development in astronomy that might just change how we understand the cosmos. We're talking about the recent creation of the most accurate map of the universe to date, and the surprising findings regarding the expansion of the universe. So buckle up, as we explore these cosmic mysteries together. We're talking about the Dark Energy Spectroscopic Instrument, or DESI, which is in the midst of a monumental 5-year mission. Its goal: to construct the most extensive three-dimensional map of the universe we've ever seen. The process is fascinating. By examining individual galaxies and analyzing the spectroscopic data, that is, the array of colors and how they shift towards red, DESI can pinpoint the position of these galaxies in our 3D map. This redshift helps researchers trace the universe's expansion back a staggering 11 billion years, and perhaps even beyond. Here's where it gets even more incredible: DESI observes 5,000 galaxies every 20 minutes, totaling 100,000 galaxies each night. That's millions of galaxies over the course of the survey. Join me as we delve into this cosmic journey and uncover what these discoveries tell us about the fate of our universe. Every year, as researchers delve into these cosmic studies, they stumble upon discoveries that are, frankly, a bit mind-boggling. Today, we're going to uncover some of these findings. But first, let's take a moment to understand the measurement techniques that not only enhance our current understanding of the universe but also shed light on its behavior shortly after the Big Bang. Understanding how we measure the universe's expansion is crucial. The technique involves an intriguing concept known as baryon acoustic oscillations, often referred to as cosmic bubbles. These bubbles formed right after the Big Bang, and understanding them is key to deciphering the early universe's mysteries. Imagine the universe in its infancy, a mere few thousand years old, so blisteringly hot that atoms couldn't yet form. At this time, the universe was a vast expanse of energy, setting the stage for the creation of everything we know today. These cosmic bubbles, or pressure bubbles, emerged during this intense period and have left an imprint that scientists can still observe and study. For a more visual explanation, I've included a video from Castro that brilliantly explains this concept. You can find the link right below in the description. Now, let's dive deeper into how these bubbles help us understand the expansive dance of galaxies and the future trajectory of our universe. Imagine the nascent universe, just a few thousand years old and unimaginably hot. In this extreme heat, light itself couldn't traverse the cosmos. Instead, it was a period where the universe somewhat resembled a fluid. Though light was trapped, pressure waves were free to roam, pulsing outward from points of density. These weren't just any waves, they were the precursors to the structure of the universe as we know it. Initially small, these waves expanded outward, growing into massive waves of density within this sea of pure energy. As the universe began to cool, a monumental change occurred around 379,000 years after the Big Bang. It finally became cool enough for the first atoms to form, a pivotal moment we now have evidence of through what we see as the cosmic microwave background, CMB. This period, known as recombination, marked the transition from pure energy to the formation of actual matter. The waves of pressure that had been shaping the universe suddenly froze in place as matter formed. These waves ceased moving but left behind a signature, a pattern of unusual densities scattered throughout the universe, visible as distinct bubbles. This cosmic phenomenon set the stage for the universe's grand architecture, and each of these bubbles tells a story of the universe's energetic youth. Let's dive deeper into how these cosmic relics continue to influence the structure and fate of our universe. Imagine each of these cosmic bubbles as tiny pockets scattered throughout the universe, each containing a bit more matter than its surroundings. These are what we call baryon acoustic oscillations, and they're not just filled with a bit more gas, but also a higher concentration of galaxies, essentially, a bit more of everything. Interestingly, by measuring the distance from the center of these bubbles to their outer edges, we can start piecing together the puzzle of how the universe has expanded over time. It appears that as the universe grew, so did these bubbles, maintaining a relative uniformity in size regardless of where they are located in the cosmos. By observing these bubbles across various parts of the universe, we can gauge the rate at which the universe has expanded. The trick to uncovering this cosmic growth pattern lies in observing as many galaxies as possible. This allows us to pinpoint where these bubbles are and observe how they have evolved over time. Recent studies, particularly using the Dark Energy Spectroscopic Instrument, DESI, have tapped into the power of galactic clustering. Researchers have managed to determine the average size of these cosmic bubbles and track their growth through the ages, offering us a clearer view of the universe's expansive journey. Tracking the expansion of the universe over the last 11 billion years is no small feat. Just take a look at this image. What you see are overlapping baryon acoustic oscillations, making the task of observing them quite challenging. Yet, despite the apparent chaos, the findings we've uncovered align closely with what we anticipated, presenting a vivid tapestry of cosmic development. One of the most astonishing revelations of 2023 was the discovery of one of these acoustic bubbles, not in some distant corner of the cosmos, but practically in our own galactic backyard. Surprisingly, this bubble is much larger than anything we expected, and as of now, it defies explanation. If you're curious about this fascinating discovery, check out the video linked in the description. We'll dive deeper into this topic as more updates become available. These baryon acoustic oscillations are like the symphony of the early universe. Their unusual patterns led to the formation of dense areas from which galaxies, stars, and eventually planets emerged. It's as if for the first 370,000 years, the universe was composing a grand cosmic symphony. This concept echoes J.R.R. Tolkien's notion of the universe beginning with a song, hinting at the poetic and interconnected nature of all cosmic phenomena. These discoveries aren't just scientific, they're a reminder of the lyrical beauty underlying our universe's formation. Exploring the cosmic landscape reveals some fascinating parallels to the idea of the universe as a grand composition, a symphony that played its first note 13.8 billion years ago. Today, we're left with the echoes of that initial melody as the universe continues to expand. Interestingly, it's quite probable that our own galaxy sits within one of these denser regions filled with an abundance of matter and gas. To refine our understanding and enhance the accuracy of their cosmic map, researchers have recently employed an innovative method using around 450,000 quasars. By examining how the light from these distant quasars interacts with the interstellar gas it passes through on its journey to Earth, scientists can map the density of this gas. This process not only sharpens our map but also enriches our comprehension of the cosmic structure. This advanced mapping technique has led to the creation of what scientists call a cosmic ruler. This tool is pivotal for measuring distances across space and, crucially, for tracking the universe's expansion over time. This measurement is completely independent from other methods such as analyzing the cosmic microwave background or observing specific types of stars like Cepheid variables. These disparate measures allow researchers to derive independent estimates for the rate of cosmic expansion and compare these findings, providing a more nuanced understanding of the universe's grand scale and its ongoing growth. The mysteries of the cosmos often start where our measurements begin to puzzle us. Recent data, drawn from observations of 6 million galaxies and approximately 500,000 quasars over the last 11 billion years, has begun to challenge what we thought we knew about the universe's expansion. This vast study suggests that while the universe is undoubtedly expanding and accelerating, there might have been a slight deceleration in recent eons compared to a few billion years ago. To put it another way, the Hubble constant, the rate at which the universe expands, might not be so constant after all. There appears to be some flux in its value over time, an issue that has sparked debates among astronomers and has been dubbed the Hubble tension. What you're seeing in these charts are various measurements of the Hubble constant from the last decade. While they generally hover around similar values, they are distinctively different and often conflict with each other. Furthermore, observations from different parts of the universe suggest that the Hubble constant might even vary by location, adding another layer of complexity to our understanding. As of now, there's no clear explanation for these discrepancies. Here, I'm showing you just a snapshot of the latest findings. Even realized the universe's expansion was accelerating, a discovery so groundbreaking that it earned the Nobel Prize. We now attribute this acceleration to what we call dark energy, a concept that has only been part of our cosmic vocabulary for a little over 2 decades. And yet, there's still no definitive explanation for it. Intriguingly, data indicate there was a significant surge in the universe's expansion about 6 billion years ago, as evidenced by diagrams from NASA. This suggests that whatever is driving the expansion, referred to as lambda in the equations, might not be a constant force at all. Recent findings add another layer of mystery. Although the universe was speeding up 6 billion years ago, it appears to have slowed down in more recent times. This raises the possibility that what we're dealing with might not be a constant but could be particle-like, with varying concentrations across different parts of the universe. Or perhaps, we're facing a phenomenon that defies our current understanding entirely. Whatever the case, the data clearly indicates that something significant is happening, challenging our observations and theories about the cosmos. In the vast arena of space, we have observed millions of galaxies that not only confirm but underline some of the most detailed and robust analysis of the cosmos to date. The findings, derived from the largest datasets we've ever compiled, are both thrilling and a bit unsettling. They point to fundamental issues within the widely accepted cosmological model known as lambda CDM, with lambda representing that elusive constant we've been talking about. Fortunately, our quest for understanding isn't over yet. The ongoing survey is set to continue for at least another year, with the next major data release scheduled for late 2025. This upcoming trove of data is expected to either solidify our current understanding or potentially lead us to new, groundbreaking discoveries. From the calculations made so far, it appears that the acceleration of the universe could be pegged at approximately 67.97 kilometers per second per megaparsec, which intriguingly sits close to that common red line value for the Hubble constant observed in some studies. However, this is in stark contrast to the majority of other observations, which suggest a faster expansion rate of about 73 kilometers per second per megaparsec. In the intriguing world of cosmology, every new observation can redefine our understanding of the universe. Recent observations using nearby supernovae and Cepheid variables, a type of star that is relatively close to us, consistently suggest a Hubble constant of about 73 kilometers per second per megaparsec. This finding, while significantly different from some other measurements, isn't quite substantial enough to overhaul our entire cosmological model. In the realm of physics, this discrepancy stands at 2.6 sigma, interesting, certainly, but not overwhelmingly conclusive. These discoveries are steering us towards potentially definitive answers to some of the universe's most profound questions. What was happening billions of years ago? What lies ahead in the cosmic future? Will the universe continue to expand at an accelerating rate, eventually tearing itself apart, or will it one day begin to contract and perhaps reset the entire cosmic process? You can explore these concepts further through videos linked in the description. For now, this release of data is tremendously exciting and underscores a critical point: modern cosmology is still in need of more studies, more analysis, and more data. We don't yet have all the answers, but the journey of discovery continues. Stay tuned for more updates as we delve deeper into these cosmic mysteries. The map we're discussing today isn't your typical road map, but rather a 3D representation of the universe. Created using data collected from powerful telescopes and advanced computer models, this map covers billions of light years, documenting not only galaxies but the vast spaces between them. This accuracy provides us with a clearer picture of the universe's structure and composition. The details in this map reveal more than just the location of celestial bodies, they show how these entities move and interact. One of the most startling revelations is that the universe is expanding at an accelerating rate, not consistent across all regions. This challenges the previous understanding that the expansion was uniform. A key player in this scenario is dark energy, a mysterious force that makes up about 68% of the universe and drives its accelerated expansion. The new map offers unprecedented insights into how dark energy works and its impact on the universe. By analyzing fluctuations in the density and distribution of galaxies, scientists can infer the properties of dark energy. These findings have profound implications for physics, requiring us to revisit some of the fundamental principles of cosmology. The non-uniform expansion could mean that dark energy is even more complex than we currently understand, or that new physics might be at play in the distant reaches of the cosmos. Looking ahead, the map paves the way for future research. Astronomers plan to use it. Galaxy clusters, the largest known gravitationally bound structures in the universe, also play a crucial role in our understanding of cosmic expansion. By mapping these clusters in detail, astronomers can examine how they have grown over time under the influence of dark energy and dark matter, revealing more about the underlying forces driving the universe apart. The creation of the most accurate cosmic map required significant technological advancements. This includes the development of ultra-sensitive detectors and long-range telescopes capable of capturing faint light from distant galaxies. The computational power needed to process this vast amount of data also represents a significant leap forward in astronomical technology. Gravitational lensing is another phenomenon that this new map helps to illuminate. This occurs when the gravity of a massive object, like a galaxy cluster, bends the light from objects behind it. Studying the bending patterns helps astronomers map the distribution of dark matter and provides further insight into the fabric of spacetime. Observations. As this map refines our observations of the universe, it also tests the validity of existing theories. For example, Einstein's theory of general relativity predicts how gravity works on a cosmic scale. The new data allows scientists to check these predictions more accurately than ever, potentially leading to new theories or modifications of existing ones. Neutron stars and black holes are among the universe's most mysterious objects. Their extreme gravity conditions and the effects they have on their surroundings are critical in the map's data. Observing how they interact with cosmic dust and gas contributes to our understanding of high-energy physics and the dynamics of galaxy centers. The public release of this cosmic map has not only excited the scientific community but also sparked interest in space science education. Schools and universities are increasingly using data from such research to teach students about astronomy and physics, helping inspire the next generation of scientists. Despite the technological advancements, interpreting the vast amounts of data from the cosmic map presents significant challenges. The complexity of translating observational data into understandable models requires ongoing collaboration between astronomers, physicists, and mathematicians. The expanding universe raises questions about its ultimate fate. Will it expand forever, or will it reach a point where it starts contracting? The insights from the new map might help answer these profound questions, as they provide more data on the rate of expansion and the forces at play.
Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.